Alright, today's study tip says if you run a race, you should practice by running. If you write on an exam, you should practice by writing. So if you want to run a race, you know the high school kids come and they run up the hill behind the college. That's where they come and practice on the weekends with their parents, right? They practice that course, they practice running that distance, they get ready for that event. They don't just say, hey, here's the hill, I'm going to think about doing that, this is what I know about the hill, and looking at the hill, right, you actually have to practice. So writing is what you do on the exam. So getting scratch paper, lots of scratch paper, writing, throwing it away, writing it again, throwing it away. No, we won't throw it away. We'll recycle it. Okay? Chapter 15. Last time we did output pressure flow part 2. These are tough topics. None of them are easy. Has it ever been easy? No. Maybe the first chapter, kind of easy. All the other chapters, not easy. You need to stay focused. Keep your study tips in mind. We are halfway through the class now. Don't get tired, okay? You don't get to rest till the end of the semester. We need to keep you healthy, okay? So you need to sleep, eat, and study. Chapter 15 is immune system, speaking of keeping you healthy. One of my favorite topics, immune system. So let's first talk about innate immunity, which means innate, what's innate mean? Like the word nativity scene, Christmas time. Innate means to be born, so at nativity scene is the scene of Jesus being born at Christmas time. Innate means to be born. So you are born with immunity. And that's also called non-specific immunity. So with this type of immunity, the body doesn't care what type of foreigner is involved. So it could be bacteria, viruses, dust, bugs, anything. And you are born with genes that are inherited, okay, to give you immunity to those basic things. So your body recognizes the difference between self cells and foreign antigens. Okay, so it knows what's yours and what's not yours. And this is part of the deal of being born with it. Okay, your body knows. So you have a list of things here that we're going to talk about that are non-specific immunity. And let me give you examples. Number 1 are physical barriers. By this we mean your skin, largest organ of the body, right? Your skin protects you from bacteria, viruses, dust, bugs, all the things we just talked about. Sweat is to cover your skin so that you don't get things into your body. Sweat is to get stuff out, right? But in this case we're talking about how it prevents stuff from getting in. Tears, when you get something in your eye, a fleck of dust or something, your eye starts to water, right? So that's to remove the foreign thing that's stuck in your eye. Saliva, get something bad, nasty tasting in your mouth, a bunch of saliva is made so that you can spit it out. Mucus, your nose, your mouth. Vomiting, so that's a natural physical barrier that you have. So if something goes into your stomach that's not good for you, your body just coughs it right back up. Phagocytes. What's phago mean? To eat, right? Cyte means cells. So these are the eating cells, your neutrophils, monocytes, macrophages. That's a rerun from your blood chapter, right? White blood cells. Some of them travel, others are fixed in their location. Okay, so some are going to leave and go off to heal places that have infection. Others are going to stay where they're made so that in case there is something there that comes into your body. Okay, so we have to call them to the area. We have a group of proteins called chemokines. They're actually hormones. They're released from tissue that is damaged to attract phagocytes to the area through a process called chemotaxis. Taxis like a taxi, right? To take you somewhere. So this chemical is to take things around. Phagocytes move out of capillaries through fenestrations by diapedesis. You should know the word fenestration. You should know diapedesis. If you don't, look them up. Okay, that's anatomy. So here we have the neutrophil in the capillary. Remember, the capillary wall is very thin, just one cell thick, endothelial cells. Neutrophil rolls along and binds to there's a signal here that tells it to bind. It is going to spread out and do the little squeeze through the fenestration. This is the diapedesis part. And the pedesis is like the word pedestrian, so it means feet. So like the cell grows microtubules actually, so that it can get through here into the interstitial fluid, get through the fenestration. Then when it gets there, it's going to have phagocytosis. In this case, they're showing a bacteria, could be a virus, could be anything foreign. Okay. These are the phagocytic cells and their locations. So we have neutrophils mostly in your blood and all your tissue, the monocytes in the blood, the tissue macrophages. All tissues, including spleen, lymph nodes, bone marrow, everything has macrophages. Macro means big, right? So they're the big ones. Kupffer cells are in the liver, alveolar macrophages, alveolus, right? That means lungs. And microglia are in the central nervous system. So your body is pretty much covered with innate immunity with these guys. The innate, slide number 3. Next we have fever. So when there is fever, that's the body's way of trying to fight off something, right? Phagocytes release pyrogens. Pyrogens are proteins that the body make that changes the thermostat of the hypothalamus. So remember, the hypothalamus is in charge of body temperature, and with the fever we increase the temperature. Oops, I don't want to go on yet. The purpose of the increasing of the temperature is to disturb the foreign bacteria, or whatever it is. Bacteria is usually what you get when you have fever. A cold doesn't really give you a fever so much. Lots of runny nose and other things like that, of course, because of all the increased blood flow to the area to bring in neutrophils, right? To bring in phagocytes. But with fever, it's usually bacterial infection. That's a clue. And it makes total sense that you get sick and your body heats up trying to kill it and you feel tired. You should not just run to the Tylenol when you get a fever. Okay, so if you take the Tylenol, what does it do to your fever? It reduces it. It is a fever reducer. That is true. And then you can go to work. And then you can go to school. And then you can cook dinner. You can do all those things. But the fever is gone. And that is not helping you heal. Not helping you recover, right? So when you get the fever, you feel tired. You want to lay down. Excellent, right? You should lay down if you have a fever. If you are sick, you should lay down. You feel hot. You feel tired and achy. Perfect. Okay, just think of how a fever is actually a really good way for the body to fight something. And most people say, oh, fever, over 100, take medicine. I'm not a believer in that. I think fever of 101, 102, and kids especially, they get fevers all the time. Totally normal. Now there are some times where kids get really high fevers and it causes a problem where they have convulsions. Okay, the 105 is getting too high probably, yeah. But 101, 102, the kid feels sick, perfect. You want the kid to lay down, right? You want them to rest. You want them to have some water and stay hydrated. Think about that. Think about how people over-medicate the fever when it's really maybe not necessary. 4. Interferon. Interferon is released from virus-infected cells in your body. Okay, so your body gets infected by a virus. Interferon is released from that cell. This is way cool, huh? Then this triggers the nearby cells to produce a virus-blocking enzyme. How's that? That is awesome. Enzymes block the virus from using the cell as a host for replication. So one of your cells gets infected and it saves the neighbors, right? By producing virus-blocking enzymes. Okay, next we have inflammation. Any foreign material or tissue damage turns it on, meaning inflammation. Chemicals are released from the tissue that turns on several events. So it could be foreign material, like, shoot, a thorn. Let's say you fell into a cactus, okay? Tissue damage, maybe You sprain your ankle. Okay, all that causes inflammation. You can think of, even in springtime, right? You get allergies, right? That's inflammation in your nose. Macrophages in the area begin to eat. So phagocytosis from the macrophages that are located in the tissue. Local vasodilation causes increased blood flow to bring more cells to the area. Very good, right? By more cells, we mean white blood cells. The mast cells, another type of white blood cell, releases histamine. Histamines increase capillary permeability, and that makes it easier for the podocytes, right, to get through. The diapedesis with those neutrophils. Right, think about that. Increase capillary permeability so that those things can squeeze through into the tissue, into the interstitial fluid, and of course that makes everything swollen, red, warm, right? If you cut your finger later, it hurts, right? There's pain. If there's an infection, there's pus, which you know is a good thing actually, right? I know when you get a blister or something, you want to poke it, right? And people do, that's fine. But the purpose of that is to bring in all those good white cells. Next, natural killer cells, love that word too. Non-specifically destroys virus-infected cells and cancer cells. Did you know that daily cells mutate and become cancerous every day? But they are destroyed, so your body has the ability, the innate ability, right, born with it, to have natural killer cells to destroy cells that are not dividing correctly. So the way those work is they lyse the cell membrane. Lyse means to cut or break. Oops, I don't want to go there yet. And then, of course, the whole foreign cell just breaks up and falls apart, right? It's not actually foreign. That's the problem with cancer, is it's our own cells, right? That's why it's so tough for us to cure cancer, because the cells actually are not detected as foreign. They're detected as our own. But they are not dividing, so the inside, of course, we don't know how to really attack it, but if we could find the inside and see that the DNA is not dividing correctly, then we could really get at it. Next is called complement. Complement is a complement to, meaning in addition to or helpful to, antibodies. Now, antibodies in this picture are the green upside down Y-shaped thing. So this is showing a bacterium, the bottom with the plasma membrane. This is the antibody. It's a protein. We'll talk more about those. Those antibodies are specific. So we're not going to talk about those now because we're working on innate or non-specific immunity. But when there are antibodies, they act as flags to call in these proteins called complement proteins. And a whole bunch of them come in together. Your body makes these proteins. And then when they all get together, they make a complex that actually puts a hole. Look at this. These are the proteins that your body makes and puts here into the foreign bacteria. And then when you put a hole, all the water comes rushing in where the solutes are higher on the inside. So this is osmosis. So the water comes rushing in and the whole thing explodes. That's way cool. So this is called complement. It complements the action of antibodies. It's activated by foreign carbohydrates on pathogens, which is what the example I just showed you, that's non-specific, or exposure to antibodies. So if the antibodies are there, then it's specific immunity. When they are activated, the proteins build a pore in the membrane. The pore is called the MAC, membrane attack complex. I of course enjoy it when doctors and researchers name things like this, because that is interesting and people remember it, right? There is an osmotic influx of water. The cell bursts when it swells up and explodes. Okay, that's it. 7 things for innate immunity. Let's talk next about adaptive or specific immunity. So this type of immunity is built over time as exposure to foreign antigens encourages the body to make antibodies, and it requires lymphocytes. So this is like something you are not born with, but your body builds up immunity. So you can think about this one like the chicken pox. When I was a kid, we all got the chicken pox. When my mom was a kid, they all got the measles. And then your body builds up immunity so that after I got the chicken pox once, I don't get it again. The same is true for every cold that you get. Your body builds up immunity to that cold, and you will never get that cold again. I don't know if you know this, but every cold that you get every winter is different than the one you got before. So little kids are always sick, right? They always got their little snotty runny nose. They're always sniffing and wiping their noses on their sleeves, right? That's because they haven't seen all of those colds before. So every year my kids were little, they had colds every 2 months. And of course, triplets, right? One got it, and then the next one got it, and then the next one got it. So like they'd all be sick for, a couple weeks. And we'd be healthy and then get it again, right? Whereas I only get one cold a year. And now that they're older, they don't get it every 2 months. They get maybe 2 or 3 colds a year. And eventually they'll grow up, be adults, and they'll probably get one. By the way, you get more colds if you don't eat right and you don't sleep well. So it's all related to being good and healthy. Sometimes adaptive and innate overlap each other, like inflammation and complement are both used in both types of immunity. So sometimes they overlap, but sometimes we can divide them, so I'm teaching you both ways. Okay, life of a B cell. This should be blank on your page, right? I want you to just listen to me, and then after I read this to you, then I want you to write it down, okay? You can pause it after I read it. So your B cells begin as stem cells in your bone marrow. Then we're writing like the life of a B cell, okay, with pathway. Then they stay in the bone marrow where they become mature B cells. Okay, just listen, don't write it now, okay, because I want you to see it. They gain receptors. So receptors are proteins in the plasma membrane that notice specific viruses. Okay, so let's say then it's sitting around and it goes out into the lymph and the blood and it travels around waiting. Let's say it's made for virus 1842. Okay, give it a number. 1842. Virus 1842, it's waiting, and sure enough, somebody sneezes, they touch their nose, and they grab the handle on the doorknob, and then you come in right after. You're exhausted, you didn't sleep last night, and you've been studying so hard for your physio class. You are weak, okay? You grab the doorknob, and then you go into class and you rub your eye because you got something in your eye. Okay, you get it. Okay, you get virus 18, what do we say? I don't even remember my numbers. I make this stuff up. 1820. Finally, your body is introduced to virus 1820. Hooray! It then becomes an activated B cell. That mature B cell becomes what we call activated and then divides to make plasma cells, which is the number one job of your B cells, is to make antibodies. And second, they divide to make memory cells. Memory cells remember. So the next time someone sneezes, touches the doorknob with virus 1840, you don't get it, okay, because you have a bunch of memory cells to attack it. So we'll talk about that more in a few minutes. The antibodies we'll talk about more too. So we have the life of a stem cell, of a B cell begins as a stem cell. Write this down. Pause the show. Now you write it down. Okay, next is a picture that kind of represents this whole story. This is showing the B cell. There's the antibodies, the antigens. Hooray, right? We finally see it. And then they divide to make plasma cells. Plasma cells, they show with all these Y's coming out, right? These are the antibodies. Okay, the memory cells sits here and remembers, so you have a bunch of them. You may never see that virus again, but your body has a whole army of them to prepare you for the future. And what else do we have here? Oh, notice that these antigens bind to the tip of the antibodies. Okay, that's the spot where they bind, and I'll show you a picture of those in more detail. Okay, so B lymphocytes or B cells work through a process called antibody-mediated immunity. I think we might have done this in lab a little bit, talked about this. Antibody-mediated immunity. That means that they work by using antibodies. Okay, so B cells have receptors to notice foreign antigens. Usually these are proteins of foreign viruses, bacteria, or allergens. After recognition of the matching antigen, the B cells divide and clone. They become plasma cells or memory cells. Right. Okay, any questions? The antibody structure. This is showing the Y-shaped thing. So it's actually a protein. Your body makes it in the B cells, right? All these antibodies have, like the top of the Y has the spot here that it's like the lock and key, like we were talking about enzymes. Lock and key fit to the foreign antigen. So the plasma cells make antibodies, and each antibody has 4 polypeptide chains, 2 heavy and 2 light. And they call them heavy, the ones on the inside. They call them light. I think it's because how they stain when they look at them. And I forget what tool they use to label these. Proteins are very, very small. You can't look in a microscope, right? You won't see it. You'll see a cell, but you won't see a protein. What else do I want you to know here? Each one is different. This is the most amazing thing, is that antibodies that you have for virus 1840, you then have one for 1841, 1842, and 1843. You might have one for a worm that infects people, in foreign countries where they don't have clean water. You make it too, but you actually will never need to use it. Okay, but your body comes made with all of these B cells ready to attack any possible thing that might come into your life. I think that's incredible. So about antibodies, their technical term, by the way, is immunoglobulins. Okay, immunoglobulins. They are proteins. There's a whole bunch of them, 100 million trillion antibodies in your body. Don't even ask me what that. Wouldn't even know how to write 100 million trillion. They attack a few million different antigens, and like I said, you won't see most of those in your life, right? You'll see just a few. And you are very lucky. You live in a nice clean place. I mean, not clean like maybe your clothes everywhere, right? Dirty laundry and dishes. I mean healthy, clean, right? We have clean food, we have clean water, we have a great system for flushing away the toilet water, all that stuff. We're really lucky to live in the United States. Really lucky. The variety is made by combining heavy and light chains, okay? Plus this change in the protein structure. So the function of the antibodies is, one is called opsonization. This is to signal phagocytosis. 2 is agglutination, which you already know that word from when we did blood, right? That's the clumping. And 3 is to signal complement. Okay, those are the functions of the antibodies. So we saw one in signaling phagocytosis, I'll talk about more. The clumping we saw in blood, and signal complement we did earlier. Okay? Memory cells. They remember the antigen if you see it again in the future. The first time is called the primary response. What do you think the second time is called? The secondary response. It's a more rapid, potent, longer lasting response. Often you see no symptoms of the foreign antigen. Okay, so if someone exposes you to that virus, that cold virus again, you won't even get sick. You won't even show a runny nose, nothing, because you've already had it. So this is the picture in your book called Primary and Secondary Immune Response. So the primary response is, this is looking at weeks after exposure to antigen on the bottom. On the left side we're looking at plasma antibody concentration. So notice it takes a while at the first response in the blue line to get the antibodies built up, right? Then when you are exposed a second time, boom, you got all those memory cells there, releasing tons of antibodies so fast, and they rocket sky high that you don't even get sick. You wouldn't even know that you were exposed to it again. Okay? So then this takes us to T cells. This should also be blank, so you can listen, then you can write it. Okay, life of a T cell. Begins as a stem cell in the bone marrow, same beginning. Now, a little different, it's called T cell because it goes to the thymus. So unlike the B cell, which stays in the bone, that's how I remember, B for bone, T for thymus. They also become mature T cells. They gain receptors for virus 1840, okay? Go to the lymph and blood, and then they wait, and they wait, and they wait, and they wait, and hooray, they're introduced to their antigen, and now it becomes what is called a sensitized T cell. Okay, it has a little different name. And it becomes different things. It becomes the helper T cell, which you may have heard of before, and we'll talk about that. Killer T cells, love that word. Those are the cytotoxic T cells, and the regulatory T cells. It also becomes a memory cell. So just like the B cells, we make a whole army of memory T cells so that the next time we don't get sick, right? Okay, so let's talk about how each of these works, okay? First of all, the action of the T cells in general is called cell-mediated immunity. So that we had antibody-mediated immunity for B cells. Now we have cell-mediated immunity. This means that they directly attack a foreign cell. Okay, so they directly attack. They mature in the thymus with a hormone called thymopoietin. They recognize self-antigen presenting cells. Self-antigen presenting cells. So let me show you a little video on this to show you what this means, okay?
Antigens are processed differently, depending on whether they originate within or outside the cell. Proteins produced within the cell, such as viruses or self-proteins, are broken down into fragments. Fragments of foreign proteins are antigens. The antigens are then transported into the rough endoplasmic reticulum. The antigens combine with class I MHC molecules. The combination is then transported to the Golgi apparatus and from there to the plasma membrane. Foreign antigens presented on class I MHC molecules stimulate cell destruction by activated T cells. Self-antigens are not recognized by the T cells and do not stimulate cell destruction. A different process occurs if the antigen originates outside the cell. Phagocytes, such as macrophages, ingest foreign particles, such as viruses and bacteria, by endocytosis. The foreign particles are broken down into fragments within a vesicle. The vesicle containing the foreign fragments fuses with vesicles from the Golgi apparatus containing the class II MHCs, and the two structures combine. The MHC class II antigen complex is transported to the plasma membrane. The displayed MHC class II antigen complex can stimulate other immune system cells to respond to the antigen.
This picture from your book shows what we're kind of showing in the video. Here we have a macrophage eating the foreign particle through phagocytosis. Then it sticks it out, a little piece of red here, this little triangle, sticks out a piece on the green part, which is called the MHC molecule, major histocompatibility complex. Okay, so a little piece of your own protein on your macrophage with a foreign antigen. Then the helper T cell comes in with two receptors, one that notices you and one that notices the foreign thing. So it got this because the helper T cell got these receptors, right? In the previous picture we learned about how it got the receptors. And when it makes a match, look at this perfect match, right? A fit and a fit, then it's going to become activated to call in all kinds of other phagocytes and stuff to help with the destruction of the foreign particle. So this is a helper T cell. An activated helper T cell then also can help a B cell. So they're called helper because they help. The pathogen is engulfed by a phagocyte. Oh, so now that was the picture. Now we describe it. The pathogen is engulfed by a phagocyte. A piece is put onto a protein in the membrane called the MHC. So you don't have to know that it's called the major histocompatibility complex, but I thought you might want to know. And the T cell recognizes the MHC plus the antigen. Tricky. So if this is not making any sense to you, get on YouTube, find some videos, post it to the group, and we can watch it. Okay? So the types of T cells, the killer T cells release perforin. So you know your lab manual, how it has little tear out pieces in it, right? That's perforated paper. So this is a great name because it's called perforin. It makes pores in foreign cells, which then causes osmosis and destruction. The regulatory T cells prevents autoimmunity. So name an autoimmune disease. Can you think of any? The first one that comes to my mind is type 1 diabetes. Okay, where the body all of a sudden says, whoa, pancreas, islets, what are those? Let's attack. Lupus, Graves' disease. Lupus is an attack of joints or kidneys. There's different kinds of lupus. Muscular, multiple sclerosis. We talked about muscular dystrophy is a different story. That's about proteins, okay? But multiple sclerosis is about fighting off your own myelin, right? There's all kinds of them. Why does that happen? The regulatory T cells are not doing their job. Why does that happen? We don't know. We don't really understand, unfortunately. Helper T cells, 60 to 80% of the T cells are helper T cells. They secrete proteins to assist other parts of the system, like B cell growth factor, interleukins, which help T cell growth, and helper T cells are the ones that are attacked by HIV. So a lot of you might know that already about helper Ts. Okay, killer regulatory helper plus the memory. Okay, so don't forget that. There's 4 different kinds, and memory's not on the list here because I think you already know it. Alright, next, AIDS and HIV. So you probably learned about this in lots of classes, so we review it now. HIV is human immunodeficiency virus. It is a retrovirus. It has RNA. It causes AIDS, which is acquired immunodeficiency syndrome. It was first declared a disease in 1981. I remember learning about this in college, and it was still new stuff. So I was in college in the late 80s, and they were just starting to really talk about it and try to figure out how it worked and how it was spread, and now we know a lot more, luckily, about all this. HIV attacks helper T cells in the mucosa of the GI tract, and T cell counts usually are 1200 per cubic millimeter. Someone has AIDS if that number drops down below 200. Okay? People live with AIDS and HIV. They live with it. So they get it and they live with it. And before, it pretty much meant that people died. So it is getting better. This is a picture of how basic structure of the HIV. The top here, remember, viruses, they don't come with mitochondria, they don't have a nucleus, they got nothing. They come in, they need the host to make all of their parts. So it drops off the RNA, which then goes through reverse transcription to make DNA, which then gets inserted into the host DNA. So this, remember, this cell here is a helper T. There is an enzyme that converts the RNA to DNA. It's called reverse transcriptase. Then, when it's in the human body, it goes through transcription, translation, and the body, the helper T is there to make other things, right? But it's also going to be making all the parts of the virus. And then it assembles and it buds off, and here's a new virus, except there'd be hundreds of them, right, coming off. This is an awesome design. I do think that HIV is not that great of a virus because, is that possible? Because actually when a virus kills its host, that's not a very good virus. Because if it kills the host, right, and it doesn't just use it to replicate, then it's actually losing its home. So in that way, HIV should be not that great of a virus, but it turns out it's being quite complicated and a lot of people are getting it. Okay, so this is your question for today. It says, one of the most popular drugs used to fight AIDS is AZT. It's a reverse transcriptase inhibitor. How do you think it works to fight HIV? And AIDS patients often die from a type of pneumonia called pneumocystis pneumonia, which is caused by a yeast-like fungus. Speculate what type of drug can be given to help with this infection. And if you could invent a drug to kill HIV, how would it work? Which part of the physiology would it attack? Okay, so pause the show. Take a break from me talking. This is a long lecture, right? And think about what you would do. Okay, reverse transcriptase. How do you think that works? Well, here's reverse transcriptase. It converts RNA to DNA. If you inhibit it, that's a pretty good idea. That's a really good one. Where else do we use reverse transcriptase? Nowhere. We never go RNA to DNA. We always go DNA to RNA. So what's interesting is that your body even has such an enzyme as reverse transcriptase. I mean, really, why do we still have it? We must have needed it a million years ago, however long as we've evolved, but now we don't. But it still comes in handy for these RNA viruses. Kind of weird, huh? AZT is, one of my students told me, she used to work at the CVS down on the corner, and she told me that AIDS patients spend about $900 a month on drugs. So it's very expensive. I think the AZT was about $300. AIDS patients die from pneumonia, fungus. What do you give? Now, usually bacteria, you would give antibiotics. This is a fungus, so you'll give antifungal. But most pneumonia you can get rid of with antibiotics. The problem is the hospital is one of the sickest places, right? So an AIDS patient really with a compromised immune system, that's what we say, shouldn't really be in the hospital where everyone is sick. But what else can you do? And if you could invent a drug to kill HIV, how would it work? I'll let you dream what you would do. Okay? Next is active immunity. So when you are exposed to a natural pathogen, you make an army of B cells and T cells. This is called clonal selection, right? To clone means to make identical ones. Accidental exposure can happen, like a cold, like we talked about. It could be purposeful, like a vaccine. The vaccines is a whole other topic, and I happen to have learned a lot about vaccines because I had kids, and when you have kids, you have to decide what to do with vaccines. There are some dangers in vaccines, like illness, right? A vaccine is a piece of the foreign thing. So let's say it's a chickenpox vaccine. They take the chickenpox and they alter it. They either chop it or they expose it to radiation. They do different salt concentrations so that it denatures in some way. But it can potentially cause illness. So if I was teaching this at school, I would say, how many of you have gotten the flu shot? And like half of you raise your hand. And then I'd say, keep your hand up if you've gotten sick from the flu shot. And at least half the people keep their hand up. So it is possible to get sick from getting a vaccine. It's not designed to make you sick. It's designed to give you a piece of the vaccine, of the antigen, the antigen, so that you make antibodies. Some people get fever, some have severe reactions. So you ask around, and a lot of people know someone who's had severe reactions from vaccines. Injections, I don't know if you know this, include a lot of preservatives and a lot of chemicals. So it's not just a piece of the chickenpox virus. There's a whole bunch of other ingredients in it. Passive immunity are antibodies given to a person from a human. So it could be, for example, mother, like this says, mother to fetus, since antibodies are small enough to cross the placenta. We also, one of the labs on blood, that we do. We talk about antibodies given from an animal donor, so maybe from a rabbit or something like that. Those, of course, are not as effective as ones that your body makes yourself, right? So breastfeeding is another way. This type of immunity, though, doesn't last long because the antibodies are from the mother, right, not the baby. And so really those antibodies are not going to last too long. So one of the advantages to breastfeeding is that babies get those antibodies and don't get sick as much. Now, I have students who breastfeed and say their kids get sick all the time. That could be. And usually sickness goes, remember the doorknob story, right? Kids touch stuff and then they put their fingers in their mouth, and especially babies, fingers in their mouth and their ears and their eyes. And so babies do get sick really easily, even with breastfeeding. Okay, so mostly it's moms who breastfeed but send their kids to daycare, right? Because daycare, they're exposed to a lot of other kids and a lot of other people. Okay, tumor immunology. So cancer cells, we talked about this. Every day they are stocked with T cells and natural killer cells. Carcinogens cause cancer. Okay, if you smoke, please stop today. Today is your day. Okay, one of the biggest, worst carcinogens comes from a cigarette. Other carcinogens, you can look up all this stuff. There's stuff in our plastic water bottles. There's stuff in the environment. There's just all over the place. We live with it, right? We live with carcinogens in our world coming into our body, but that's okay. Okay, a little bit your body can fight, but when you add additional things like smoking to it, it just makes it harder for the body to survive. Okay, so a tumor. Sometimes there are tumors that grow maybe in someone's leg or their foot or something like that, and they just remove it. Okay, it's a clone of identical cells, and it's benign, not a problem. It stays in the tissue. The problem is when we hear a tumor being tested, maybe in the breast tissue, and we hear that it's malignant. Okay, that's the bad word. That means that it is not staying in the tissue and it's starting to leave. And then when it gets into the lymphatic system, it goes everywhere. Okay, and that's called metastasis. So some of you may be upset by hearing all these words. If you know somebody who suffered from this type of cancer, malignant means you got to get to it fast, and it's usually a stage, a higher stage. We say stage 1, stage 2, stage 3. It's higher stage the more it has spread throughout the body. Treatment of cancer includes monoclonal antibodies made to recognize receptors on tumors. So this is again what we were just talking about. What they're doing is taking the cancer cells from a patient, putting it into an animal, probably a rabbit. Unfortunately, they kill the rabbit usually. Sometimes they can bleed the animal, but as you can imagine, a rabbit doesn't make a lot of blood, right? And they take the blood of the animal and they take out the antibodies. That's what they do. And it's starting to help some people. So it's expensive, as you can imagine. Not everyone gets to have it. They're picking certain people that might work better for them and things like that. Cancer is cancer, diabetes, heart disease. There's so many that we can really do something about, right? Type 2 diabetes we can do something about. Heart disease we can do something about. But cancer, besides like smoking and some of the major carcinogens in life, it's going to be one of the hardest ones to cure. Immune system malfunctions. This is autoimmune diseases. So see the book, we kind of talked about this. Also, sometimes you have allergies. I have a son who's super allergic to cats. Oh my gosh. He goes into, my husband too. They go into a cat house. They go into a house with a cat and they say, there's a cat here. Like they know. Both my husband and my son know. They're like, there's a cat in this house. And so, is there a cat? No. Oh yeah, he's way upstairs and back in our bedroom. He hides there. So like that's enough for these hypersensitive people. So we have like, the crazy peanut allergy, right, that we talked about where you need a shot of epinephrine. It's just some people are allergic to bee stings, mold, dust, fur, the cat, dogs, food, pollen. So my my kids are getting older. starting to get more allergies, I've noticed, as people get older. And my daughter now said, we had shrimp when we went out to eat. She said, Mom, my throat feels, what'd she say? Cloggy. That's the word she used. So she's 12. She feels cloggy. I said, what does that mean? She said, it means I can't really, it's like, I can't swallow real well. Like, it feels like there's like fluid in there, you know? And I said, oh, what are we eating now? Seafood. And so, of course, that's one that a lot of people have, seafood. So it's important now that we're careful for her. And she's in tune, luckily, to her body. But little kids, of course, are not. So you got to be careful for those. The allergic reaction, allergen, is seen by the B cell. The B cell makes antibodies. The antibodies turn on the mast cells, which make histamines, and then you get the inflammation, which is the clogginess, right? So she was getting inflammation in her throat. That's what she was feeling. You can take antihistamines, of course, which work against, right? Two types of allergies. Immediate hypersensitivity, which means that, like the shrimp, okay, the plasma cells produce IgE antibodies. There are 5 kinds of antibodies. And you can write this down because I didn't write it down. M-A-D-E. This is how I memorize it because it's actually the word made, right? M-A-D-E and G. So made G. So that's how I remember. You have immunoglobulin. IG stands for immunoglobulin. M-A-D-E and G. So the plasma cells make E. Now remember that they are all different. They notice different things. But there's these general 5 categories. Antibodies signal mast cells to release histamines, your friend again. Smooth muscle constriction of the airways can happen. So this is what happens to my son when he gets around the cats. He starts wheezing immediately. And he can only stay, I have to give him a Benadryl before he goes to the friend's house with a cat. And I don't even know if it's worth it. I mean, it's fun to play with a friend, but really, to come home with, be wheezing is probably not worth it. Eosinophils, which are a type of white blood cell, are attracted to the area. And then too much, of course, leads to anaphylactic shock, which luckily I haven't seen at my house. And then the delayed hypersensitivity, like poison oak. How many of you have had poison oak? How many of you don't know if you're allergic to poison oak? Yeah, so let me tell you that most of us are allergic to poison oak. And some of you think you don't, probably just haven't walked through it very much, okay? You're not exactly out there hiking probably every other day. But this is delayed, so it involves T cells 2 to 3 days, maybe after exposure to poison oak. You will get the rash. So if you don't know what it looks like, you can do a little research online to see what the rash looks like. It's red, swelling. My parents live up in the woods, and their dog goes out, and the dog gets it on his fur, and then my mom loves on the dog, and she sent me a picture of her face with poison oak on it. I was like, what were you doing? She said, I was rubbing the dog. She's loving the dog. She got poison oak on your face. So poison oak has oil in the plant itself, and if you don't know what poison oak looks like, check it out. And there's that little story that says leaves of 3, let them be. Okay, so it has leaves of 3. It's a small shrub-like plant, and there is tons of it in the Santa Cruz Mountains. Tons of poison oak in our evergreen hills. Okay, so be very careful if you don't know about it. And it doesn't always have leaves in the wintertime, but it still has the oil. So if you think you've been in it, you have to take a hot shower, and there's a type of soap you can buy at the store. You can ask for help from the dermatologist or from the Longs or CVS or wherever you shop at the pharmacy. Tell them you want the soap. Okay, so walking, hiking out in the bushes, be sure you're staying on the trail. Be sure you are wearing long pants. Okay, and don't go chomping around things that you don't know. Okay, you won't know that you got it though till 2 to 3 days before. And one of the problems with poison oak is it gets worse and worse. Every time you get exposed to it, it spreads a little more and gets a little more bumpy and a little more painful. Okay, long lecture, lots to cover. You get your whole degree in immunology, right? Fascinating. All right, we're done. Thank you.